For your whole life, 8 planets has sounded final, settled, done. But cracks are showing in that picture, and a growing number of astronomers think there might be a hidden heavyweight, way out in the dark, that changes everything. In this video, we're going to follow the clues and ask a simple question. Did we miss a 9th planet in our own solar system? You were taught there are 8 planets in the solar system, right? From Mercury out to Neptune, nice and clean. In that picture, everything important fits inside a bubble about 30 astronomical units from the Sun, roughly 4.5 billion kilometers, about 2.8 billion miles. Neptune is the outer edge, Pluto is a tiny extra, and past that, you maybe heard a vague line about some comets way out there. That version is still in a lot of textbooks, still in a lot of people's heads, and it is quietly wrong, or at least very incomplete. Here's the problem. That map basically stops at the city limits. It cuts off the real outskirts. When astronomers actually pushed their surveys beyond Neptune, not 10 or 20 astronomical units beyond, but hundreds of astronomical units into the dark, they didn't find empty space. They found more worlds, and some of them are on orbits that make no sense if the 8 known planets are the only big players. The simple that's an 8-planet diagram turns out to be just the inner part of a much bigger structure, and the outer part does not behave politely. So what is normal out there, and what is weird? Just beyond Neptune you have the Kuiper Belt, a swarm of icy bodies. Thousands of these objects have been logged. Most of them are fine. They follow orbits that are only mildly stretched, only mildly tilted, and they are still clearly under Neptune's gravitational control. Their average distances from the Sun, what astronomers call the semi-major axis, are maybe 40, 50, maybe a bit more astronomical units. Neptune can still bully them, can still push and pull their orbits over time. But then, there is a small group that does not fit that pattern at all. These are the extreme trans-Neptunian objects, ETNOs. Their average distances are not 50 or 60 astronomical units. They are 250 astronomical units and more. That means their typical distance from the Sun is over 37 billion kilometers, roughly 23 billion miles. At those distances, Neptune is far away and very weak. These objects are not just far, their orbits are stretched into long ellipses and tilted, and when you plot the directions of those orbits in space, they seem to be pointing the same way, which is exactly what you do not expect from random debris. You might say, maybe we just got unlucky, maybe our small sample happens to look aligned. That is a fair question, and for a while people worried about exactly that. Then teams like Trujillo and Shepard, and later Batygin and Brown, did the boring, careful part. They measured the actual orbital angles. They looked at where each orbit comes closest to the Sun, and which way in space that point is oriented. They also looked at how each orbital plane is tilted relative to the average planetary plane. If nothing special is going on, those directions should be scattered. They should look random over billions of years. Instead, the most distant ETNOs cluster. Their closest approach points all sit in roughly the same region of space. Their orbital planes lean in similar directions. In simulations where you only include the known 8 planets and the Sun, that pattern gets smeared out over time. Gravity from the known planets, plus passing stars and the galactic tide, should erase any neat lineup. The fact that we see a strong pattern today means either we are living in a strange statistical fluke, or there is an ongoing, steady influence that keeps that pattern in place. So how unlikely is it to be just luck? When the teams ran numerical simulations with randomized orbits, and then applied the same selection effects that real surveys have, the odds of getting the same level of clustering purely by chance came out very small, much smaller than you would be comfortable calling normal noise. Different groups get different exact numbers, but they keep landing in the "this is suspicious" range, not the totally fine range. That's when the idea of a hidden massive perturber stopped being a casual remark and became a serious working hypothesis. Then you hit the next question, which is very basic but very important. Could Neptune, or any of the known planets, do this job by itself? The answer is no. Neptune's gravitational reach is strung out to maybe 50 astronomical units, about 7.5 billion kilometers, roughly 4.7 billion miles. Beyond that, its control drops quickly. At 500 astronomical units, the Sun's gravity at that distance is already around 250,000 times weaker than it is at Earth. Neptune's influence on an object that far out is tiny. A Pluto-sized dwarf planet does even less. To herd these ETNOs into aligned, long-lived orbits, and keep them that way for billions of years, you need something with much more mass. That something looks a lot like a missing planet. The modelling points to an object with several times Earth's mass, strong enough to act as a shepherd for distant ice balls, but light enough that we have not already seen it by accident. In other words, not a second Jupiter, but a super-Earth or mini-Neptune. And this is where the stakes really jump. Because if that planet exists, it is not a small adjustment to the solar system, it is a major new component. Think about what those numbers mean. A 5 to 10 Earth mass planet, maybe 2 to 4 times Earth's radius, on an elongated orbit with an average distance somewhere between 400 and 800 astronomical units. That puts its typical distance at least 60 billion kilometers, around 37 billion miles. Its closest approach might be in the 200 to 300 astronomical units range, maybe 30 to 45 billion kilometers, 19 to 28 billion miles. Its farthest point could be near 1,000 astronomical units. That is not a minor rock. That is a large, cold world that would dominate the outer architecture of the solar system. If it is there, it would help dictate how distant comets move, how some small bodies get fed into the inner system, and maybe even contribute to why the Sun's spin axis is tilted about 6 degrees relative to the average plane of the planets. It would connect our solar system to the exoplanet universe, because super-Earths and mini-Neptunes are common around other stars, but so far missing in our own catalogue. With Planet 9, suddenly we have one, just much farther out than anyone expected. So now you are stuck with a sharp choice. Either the strange orbits of the most distant objects are a coincidence plus observational bias, and there is no hidden planet, or there really is a massive world, hundreds of astronomical units away, that has been reshaping the outer solar system for the billions of years, while we stared at the inner region and thought the story was complete. Both options force you to rethink the simple 8-planet picture you learned first. If there is such a planet, there must have been a first warning sign, a single object whose orbit was so extreme, so detached from Neptune, that it made astronomers stop and say, okay, this one cannot be explained by the standard model, so which distant world was that first alarm bell, the one that pushed people toward the idea of a 9th planet in the first place? How do you know the solar system map is broken, not just incomplete, but actually misleading about what's really out there? You look for the first orbit that flat out refuses to fit the rules. That first serious red flag was a small distant world called Sedna. Sedna was discovered in 2003, and straight away its orbit looked wrong. At its closest, it comes into about 76 astronomical units from the Sun, so about 11.5 billion kilometers, roughly 7.1 billion miles. That is more than twice as far out as Neptune. At its farthest, Sedna swings to nearly 1,000 astronomical units, up to around 150 billion kilometers, about 93 billion miles. One single loop takes around 11,000 years. For comparison, Earth does its lap in 1 year, Neptune in about 165 years. Sedna is on the kind of orbit where, if humans had discovered it in the Stone Age, it would still be on basically the same part of its path today. Now here's the key point, and this is why Sedna got everyone's attention. Sedna never comes close to Neptune. Its closest approach distance, that 76 astronomical units, keeps it safely away from the zone where Neptune can give it a big gravitational kick. Most of the scattered Kuiper Belt objects, the ones with the stretched orbits, can be explained as former Kuiper Belt residents that Neptune tossed around in the early solar system. Sedna does not fit that story. Neptune cannot be the one that threw Sedna onto its current path. The math does not work. So then the question becomes, who did it? Sedna looked like it belonged to a hidden population, an inner Oort cloud, not the classic Oort cloud way out at thousands of astronomical units, but a closer shell of objects that have been lifted off the planetary zone and parked in distant detached orbits. To get an object from the Kuiper belt onto a Sedna-like path, you need a strong disturbance early on. That could be a close passing star when the Sun was still in its birth cluster, or a massive unseen planet in the outer system, or some combination. Whatever it was, Sedna was the first clear message that the outer solar system had a more violent, more complex past than the simple 8-planet cartoon suggests. You could still argue, okay, Sedna is weird, but every system has outliers, maybe it's just one strange object with a special history. So the next step is obvious. If this is a real structured population, Sedna should not be alone. You should find cousins that share the same kind of detached, far-out orbit, and ideally you should see some kind of pattern in how those orbits are arranged in space. So did we? The next big piece dropped in 2012 with the discovery of 2012 VP113, nicknamed Biden. This object also never gets near Neptune. Its closest approach is around 80 astronomical units, even farther than Sedna's, so about 12 billion kilometers, around 7.5 billion miles. Its far end is around 450 astronomical units, close to 67 billion kilometers, about 41 billion miles. Different numbers from Sedna, yes, but when astronomers plotted both orbits in 3 dimensions, something interesting showed up. Sedna and 2012 VP113 have their closest approach points, their perihelia, in roughly the same part of the sky. Their orbital paths are tilted and oriented in similar directions. In plain language, they are both on long, stretched ellipses that dive in toward the Sun on the same side and lean the same way. With just one object, you can't talk about a pattern. With 2, you can start to get suspicious, but you still have to be careful. 2 points can always be a coincidence. To make a serious claim, you need a sample, not just a couple of poster children. So now the game changes. The question becomes, what happens when you add more of these extreme objects to the plot? Do they scatter in all directions, or do they keep lining up? Over the next years, more and more distant bodies were discovered, and by the mid-2000s, astronomers had a list of around a dozen extreme trans-Neptunian objects in this category. These were objects with closest approach distances beyond about 40 or 50 astronomical units and average distances, semi-major axes, beyond about 150 to 250 astronomical units. They are the true outer system specialists, well beyond Neptune's direct grip. When researchers looked at the angles that describe these orbits, 2 of them mattered a lot. One is where, along the orbit, the object gets closest to the Sun, and which direction that point faces in space. The other is how the orbital plane itself is oriented, its tilt and its twist relative to the plane of the planets. In a chaotic outer system after billions of years, you expect those directions to be smeared out. Some objects here, some there, no strong preferred region, but that is not what they saw. Instead of being randomly oriented, the arguments of perihelion and the longitudes of perihelion of these ETNOs were clumped into relatively narrow ranges. In simpler language, both the direction of closest approach and the way their orbital planes are rotated around the Sun were clustered rather than scattered. It looked, statistically, as if something was keeping time on their orbits, keeping them in a kind of shared configuration over very long periods. Now you are at a fork. One path says, this is a selection effect, our surveys only looked in certain directions, so of course we find objects in similar orientations. The other path says, no, this is a real physical pattern caused by gravity from something we have not seen yet. To decide between those, you can't just stare at the sky. You have to build models and push them as hard as you can. So the next question is, if we try to reproduce these orbits in a computer, with and without a hidden planet, which setup matches reality better? That's where the work by Batygin and Brown comes in. They ran full gravitational simulations, not just simple estimates. Start with a swarm of distant Kuiper belt objects, give them a range of initial orbits, include the known giant planets, and let the system evolve for billions of years. First, you do it with only the 8 known planets, and the result is exactly what basic intuition says. The orbits diffuse, the angles spread out, the nice clustering washes away. In that picture, you do not end up with a tight group of distant objects whose orbits all point the same way. The pattern does not survive. Then you rerun the experiment, but this time you add a ninth planet. Give it a mass of several Earths, put it on a distant, elongated, inclined orbit, with an average distance in the hundreds of astronomical units, roughly where the observational clues point. Now let gravity work for the same billions of years. The outcome is different. A subset of the distant bodies settles into stable configurations where their closest approach directions are anti-aligned with the unseen planets. That means their closest point to the Sun tends to be on the opposite side of the Sun compared to the closest point of the big planet's orbit. The end state of the simulation shows exactly the kind of clustering that we see in the real ETNO data. So this is not just fitting one orbit by hand, it is saying, if a planet like this exists, and you give the system enough time, the distant small bodies naturally sort themselves into the kind of group we actually observe. Without the planet, you do not get that structure. With the planet, you do. That is the core of the argument for an unseen sculptor. But a good model needs more than matching one pattern. It needs extra predictions, things you did not initially build it to explain. So the next test is, does this hidden planet scenario accidentally explain other weird objects as well? When the same simulations were analysed more deeply, they showed something unexpected. Some of the test particles, the simulated small bodies, were pushed into orbits with extreme tilts of 90 degrees and even more relative to the plane of the planets, and some ended up on retrograde orbits, moving around the Sun in the opposite direction to most planets. Later, observers found real solar system bodies like this, with average distances less than about 100 astronomical units, but with very high inclinations far from the main planetary plane. These are hard to produce in large numbers if you only have the known 8 planets. In the Planet 9 simulations, they appear naturally. The distant planet stirs the orbit slowly, pumping up their tilts and changing their shapes. Then once an object's path crosses into the region controlled by Neptune, Uranus, Saturn and Jupiter, those known giants can scatter it inward or outward, locking in the high inclination. The end result is exactly the mix you see in the actual outer solar system, a background of normal Kuiper belt objects plus a minority of extreme tilted, sometimes retrograde oddballs. At that point, the data starts to look less like random noise and more like a pattern left by something specific. You have Sedna and 2012 VP113. As the early warnings, a growing list of ETNOs with clustered orbital directions, and a set of simulations where adding a super-Earth far away reproduces both the clustering and the existence of strange high-inclination objects. But there's still a crucial gap. You can describe the fingerprints, you can match them in a model, but you still haven't answered a basic question. How does a planet sitting hundreds of astronomical units away, crawling along its orbit over tens of thousands of years, physically twist and line up these orbits without ever coming close to them, and without us yet seeing it directly? So how can something you've never seen, sitting hundreds of astronomical units away, quietly rewrite orbits all over the outer solar system without dramatic close passes or big crashes? The answer is that gravity does not need to be strong, it just needs to be patient. If Planet 9 is real, and it lives somewhere between about 400 and 800 astronomical units from the Sun, it would be crawling along its orbit. One full lap could take 10,000 to 20,000 years. From your point of view, looking from Earth, it would barely move against the background stars from one year to the next, just a slow drift. But now stretch your timeline. On a million-year scale, on a 100-million-year scale, that tiny constant gravitational pull is always there, always tugging. These are not violent flybys, not sudden kicks. They are slow, cumulative nudges that orbit after orbit twist the orientation of smaller bodies and pump their orbital shapes more stretched or more circular. This kind of interaction is called secular evolution. Instead of changing where an object is right now, each tug slightly changes the parameters of the orbit itself, the tilt, the orientation in space, the eccentricity, how stretched it is. Over millions of years, those small changes add up. The orbit's path slowly rotates, like a spinning top precessing under gravity. while the object calmly keeps going around the Sun. From far away, nothing looks dramatic. In phase space, in the math, everything is shifting. That leads to the next key question, the one that connects directly to the observed pattern. Why do those distant objects end up pointing in roughly the same direction, instead of being twisted into random orientations over time? Take one of these ETNOs, a distant body with an average distance of a few hundred astronomical units on an elongated orbit. Planet 9 is on its own elongated, tilted path farther out. Over millions of years, the steady pull from Planet 9 slowly rotates the line of apsides of the ETNO. That is, the line connecting its closest point to its farthest point. The orbit's closest approach point, its perihelion, does not stay fixed. It migrates around the Sun's sky direction under the influence of the distant planet's gravity and the known giants. The crucial part is stability. Some orientations make the small body's orbit unstable, leading to close encounters with Planet 9 or the other giants, which can eject it or throw it inward. Those configurations do not last long, they get cleared out. Other orientations are dynamically protected. In the simulations, the long-lived survivors tend to settle into a configuration where their perihelion direction is roughly opposite that of Planet 9's perihelion. That is what people mean by anti-alignment. The closest point of the ETNO's orbit to the Sun ends up on the other side of the Sun from Planet 9's closest point. Once you see that, the observed clump in longitude of perihelion stops being mysterious. The ETNOs you can still see today are the ones that fell into those stable anti-aligned islands in parameter space. Everything else either got scattered away or never survived on billion-year timescales. So the clustering is not the starting condition, it is the end state, the stable outcome of being torqued for billions of years by a distant heavy planet. But there is another layer on top of that, which makes the whole structure even more robust. How do you keep those orbits in place for the entire age of the solar system, without random kicks slowly smearing them out again? Here is where mean motion resonances show up. When you look closely at the simulations, a lot of ETNO-like bodies end up in simple orbital period ratios with Planet 9. For example, the small body might complete 3 orbits in the time Planet 9 completes 1, or 5 orbits while Planet 9 completes 2. Those are mean motion resonances. They act like locking points. The average distance of the small body adjusts slightly so that, over long periods, it never has dangerously close encounters with the big planet, even though they share the same general region of space in terms of distances. You already know a version of this from Pluto. Pluto completes 2 orbits for every 3 of Neptune's. That 3-to-2 resonance is why Pluto does not get kicked out, even though its path crosses Neptune's orbit in a simple diagram. The timing is always such that they are not in the same place at the same time. With Planet 9, you push that same logic far into deep space. Resonances create gear teeth that keep ETNOs on specific tracks, maintaining the clustering for billions of years, instead of letting random gravitational bumps slowly randomize everything. Now, clustering is one thing, but Planet 9 has to explain more than just a group of orbits that happen to line up. There are also those extreme high inclination, even retrograde objects, bodies whose orbits are tilted so much they almost stand up vertically compared to the planets, or even go around the Sun backwards. Can a distant planet account for those too, or are they a separate mystery? When dynamicists include Planet 9 plus Jupiter, Saturn, Uranus and Neptune in their models, something interesting happens. For some small bodies, the same slow, secular torques that twist perihelion directions also pump up orbital inclinations. Over time, their tilt can be driven past 90 degrees. Once that happens, the object becomes retrograde. Its orbit now cuts across the planetary plane at a steep angle instead of lying roughly in it. Then, when it finally wanders close enough to the region where the known giants dominate, those planets can scatter it again, but now starting from a bizarre, almost polar or retrograde path. The result is a natural path from a distant, moderately inclined ETNO influenced by Planet 9 to a closer-in, high-inclination or retrograde centaur influenced by the known giants. That is exactly the kind of population we actually see. Objects with average distances under 100 astronomical units but wild tilts, very hard to produce in large numbers with only the 8 known planets. With Planet 9, you do not need a separate mechanism. The flipping is part of the same gravitational story. So far, this all sounds like model builders matching things they already knew. To really push the hypothesis, you need a prediction that is not just, look, this cluster looks right. You need a population test, something you can count in the real sky. That is where Neptune crossers come in. In more recent work, Brown and Batygin pointed out that if Planet 9 is there, it should not only sculpt the distant detached objects, it should also slowly drive a fraction of them inward. Over long time scales, some of those orbits should have their closest approach distances pushed down below about 30 astronomical units, where they start to cross Neptune's orbit. When that happens, these bodies become Neptune-crossing objects, with long periods but perihelia in the region of the known giants. With Planet 9 in the simulations, you get a noticeable fraction of such long-period Neptune crossers. Without Planet 9, starting from similar initial conditions, that fraction is much smaller. That turns the actual population of these objects into a statistical test, not a one-off story. If surveys keep finding more of them, in the numbers and with the properties predicted by the Planet 9 models, the case for a distant massive planet gets stronger. If they do not, the hypothesis takes a hit. So now the tension ramps up. The dynamics give you a clear set of behaviours, clustering flipped orbits, a predicted stream of Neptune crossers. The next step is obvious and uncomfortable. If this planet is really doing all of that, where exactly should it be? How massive should it be? And how on earth have we still not seen it? How tightly can you actually pin down something you have never seen, but whose gravity seems to be leaving fingerprints all over the outer solar system? At this point, the numbers are not vague guesses anymore, they are surprisingly specific. When you take the clustering of the extreme trans-Neptunian objects, add in the high-inclination weirdos, and fold in what modern surveys have or haven't found, you get a fairly tight box for Planet 9. The best fits put its mass somewhere around 5 to 10 times Earth's mass. That is in the super-Earth or mini-Neptune range, not a gas giant. Its orbit has an average distance, a semi-major axis, of roughly 400 to 800 astronomical units, so you're talking about tens to over 100 billion kilometers from the Sun, from about 25 to 50 billion miles on average. The orbit is not a neat circle. The eccentricity, so how stretched that orbit is, comes out something like 0.2 to 0.6. In plain terms, that means the distance from the Sun changes a lot over one orbit. At closest approach, its perihelion might sit in the 200 to 300 astronomical units range, around 30 to 45 billion kilometers, roughly 19 to 28 billion miles. At the far end, the aphelion could reach close to or beyond 1,000 astronomical units, heading toward 150 billion kilometers, about 93 billion miles. On top of that, the orbit is tilted by about 20 to 30 degrees relative to the plane where most planets orbit. So this thing, if it exists, is not cruising along neatly with the rest, it's on a slanted, stretched path that loops far into the dark. Those parameters are not picked to be dramatic, they're chosen because when you plug them into simulations, that kind of planet best reproduces the patterns you see in the real ETNO data. Change the mass too much, or move the orbit too close or too far, and the clustering either weakens or shifts to the wrong place. That is why people talk about Planet 9 as a fairly well-defined target, not just some big thing out there, so then the obvious question hits you, and it's a bit uncomfortable. If there really is a planet 5 to 10 times heavier than Earth, with a radius maybe 2 to 4 times bigger than Earth's, somewhere a few hundred astronomical units away, why hasn't someone just seen it already? The short answer is, because at those distances, it is brutally faint. Take that 5 to 10 Earth mass mini Neptune and park it at, say, 600 astronomical units from the Sun, around 90 billion kilometers, roughly 56 billion miles. The sunlight out there is not just a bit weaker, it has dropped off by the square of the distance. You are 600 times farther than Earth, so the light is 600 times 600 weaker. That's 360,000 times less sunlight per square meter than we get here. Even if the planet has a decent reflectivity, it is returning a tiny trickle of light. Convert that to astronomical brightness, and you end up with an apparent magnitude somewhere around 22 to 25. Pluto is typically around magnitude 14 or so at opposition, much brighter. Your naked eye, under excellent dark skies, cuts off around magnitude 6. A normal consumer camera and lens with a short exposure might reach around magnitude 11 or 12. Planet 9 at 600 astronomical units would sit far beyond that as a very faint speck that only big professional telescopes can pick up, and even then, only with careful long exposures and good conditions. So you need serious hardware, you need time on large telescopes, and you need to know roughly where to point them. You can't just sweep the entire sky to that depth in a casual way. That leads straight into the next problem. If the orbit is only roughly known, where on the real sky should you actually be hunting? The orbital fits do not only tell you the distance range, they also give you preferred regions on the celestial sphere. When Brown and others combine the ETNO orbits and run their fits, they get a swath of likely positions, not a full 360-degree ring. The best guesses put Planet 9 in a section of the southern sky, off the main galactic plane, in areas that, annoyingly, older surveys did not cover as deeply or as often. That is important. Many big surveys either focused on the ecliptic plane, where the known planets and most asteroids live, or they spent their time on the rich star fields of the Milky Way. The probable Planet 9 zone sits partly in between those sweet spots, in regions that are comparatively underobserved at the necessary depth. So it is not that every square degree of sky has been searched down to magnitude 24 or 25 for ultra-slow movers. There are real gaps, and Planet 9's best fit orbit tends to thread through those less explored patches. Even once you point the right telescope at the right sky area, the planet's motion makes the job harder. At a few hundred astronomical units out, its actual orbital speed is only on the order of a few hundred meters per second. Call it the speed of a fast car on a highway. Earth, by comparison, is moving around the Sun at about 30 kilometers per second, around 67,000 miles per hour. From our point of view, that slow, distant motion projects onto the background stars as only a few arcseconds per hour, sometimes less. For imaging, that is a headache. Between one night and the next, the speck has barely moved. Over a single long exposure, it hardly trails at all. You're trying to spot a point of light that shifts by maybe a fraction of a pixel from night to night in a field crowded with galaxies, stars, detector noise, and moving near-Earth asteroids that streak by much faster. The good news is, almost nothing else in the sky moves that slowly and that steadily in the right direction. So once you do find it, the motion pattern would be a strong confirmation. The bad news is, getting to that point is a lot of work. There is one more handle on this problem that does not rely on taking its picture at all. If you drop a 5 to 10 Earth mass object into the outer solar system, it tugs on everything else, even if very slightly. Planets do not orbit the Sun in perfect, predictable paths if there is a hidden mass messing with the gravitational field. So teams have used extremely precise measurements of planet positions and spacecraft trajectories to look for hints of such a tug. A famous example is Cassini at Saturn. For years, Cassini's orbit around Saturn and Saturn's orbit around the Sun were tracked with high precision, using radio signals and careful modelling. If there were a big extra planet inside a few hundred astronomical units in certain directions, its gravity would pull on Saturn enough to show up as small systematic deviations from the expected path. When researchers fit all that data, they can say, if Planet 9 were here, at this distance, with this mass, we would have noticed. Those analyses carve away large chunks of the possible parameter space. What they do not do is completely rule out Planet 9. The constraints mainly say that a 10 Earth mass planet cannot be too close, or in some particularly sensitive directions, without breaking the excellent match we already have between models and real planetary positions. Farther out, beyond a few hundred astronomical units, its pull becomes weak enough that it blends into the uncertainties, especially if its orbit is angled away from the most tightly monitored directions. In that regime, the ephemeres, the detailed "where are the planets now" models, simply do not have the resolution to give a clean yes or no, so right now you end up with a very specific but still frustrating picture. If Planet 9 exists, it is probably 5 to 10 Earth masses, sitting hundreds of astronomical units away in a particular region of the southern sky, moving painfully slowly and too faint for any casual survey to have nailed already. The allowed box is narrow enough to make it a real target, but wide enough that you can still miss it with limited telescope time. And that leads straight into the next, sharper question, the one that really raises the tension. If we know roughly how heavy it should be, where it should be, and how it should move, why have the biggest telescopes and the infrared sky scans still failed to give us a clear detection? If Planet 9 might be as big as 10 times Earth's mass, why haven't we just pointed a big telescope at the sky, taken a few pictures and checked this off the list? The short answer is because the combination of how faint it is and how much sky it could be hiding in is a nightmare. To see Planet 9 in reflected sunlight, you're aiming for brightness levels around magnitude 22 to 24 or fainter. That already puts it in the only serious professional telescopes need apply category. You're talking long exposures on large mirrors, not quick snapshots. Now put that requirement next to the size of the search area. The plausible orbital solution spread Planet 9 over thousands of square degrees of sky. For scale, the full moon covers about half a degree across, so its area is only a tiny fraction of a square degree. You're effectively tiling a mosaic that would cover thousands of moons worth of skin, each tile needing a deep exposure, and then you need to come back and re-image those tiles later to look for a faint dot that moved a tiny amount. Existing big telescopes can go deep, or they can cover a wide field, reasonably fast, but doing both, deep and wide, over that whole area costs an enormous amount of telescope time. Observatories also have competing science goals, weather losses, maintenance, all the usual real-world stuff. So while targeted campaigns with telescopes like Subaru have covered some of the predicted region, they have not yet blanketed the entire allowed patch down to the necessary depth and with the right cadence to catch such a slow mover. The fact that it's possible in principle does not mean it's trivial in practice. So if optical light is that painful, can we cheat by looking for Planet 9's own heat instead of waiting for a few reflected photons from the Sun? A planet, especially a mini Neptune with several Earth masses, is not just a cold mirror. Its interior is still slowly leaking heat left over from formation. Even out at hundreds of astronomical units, its atmosphere and interior might sit at something like 40 to 50 Kelvin, around minus 230 degrees Celsius, roughly minus 380 degrees Fahrenheit. That's extremely cold by human standards, but warm enough to glow faintly in the mid-infrared. In that wavelength range, you're not depending purely on sunlight, you're seeing the planet's own thermal emission. Space missions like IRAS in the 1980s, Akari in the 2000s, and WISE more recently, have scanned most or all of the sky in infrared bands that are sensitive to this kind of emission. They give you snapshots of the whole sky at different times. Teams have gone back into those archives looking for sources that appear in one survey, then shift slightly by the time of the next survey, at rates consistent with distances of a few hundred to maybe 700 astronomical units. So far, those searches have not turned up a "this is definitely Planet 9" detection. What they have done is carve away big chunks of parameter space. They rule out the idea that there's some hot Saturn or Jupiter mass object lurking a few hundred astronomical units away. They also place limits on how bright and how close a Planet 9 type object could be. In some cases, they found at least one interesting candidate, a faint infrared dot that moves just enough between IRAS and Akari epochs to be worth attention. But interesting is not the same as confirmed. That brings up the next headache. When you dig around in infrared catalogues, how do you separate a real distant planet from the huge amount of junk and confusion in the data? Infrared sky maps are messy. You've got variable stars whose brightness changes over time. You've got distant galaxies that can look like tiny smudges. You've got detector glitches, and you've got near-Earth asteroids and comets zipping through fields much faster than anything at hundreds of astronomical units. A true Planet 9 at 500 to 700 astronomical units would move only a fraction of an arcsecond per day. That's slower than many catalogue systematics, slower than the resolution of a lot of older data products. Distinguishing that from noise is hard. When a team in 2025 put out a first good candidate based on IRAS and Akari, what they had was a faint point source that seemed to shift by just the right amount between the two missions at a level that could match a distant giant. But follow-up analyses, including orbit fitting, suggested that if you interpret those detections as a single object, the resulting orbit might be too strongly tilted or otherwise out of line with the standard Planet 9 predictions. That opens the door to several possibilities. It could be a different kind of distant solar system body, it could be a statistical fluke or a subtle artifact in the data, or it could mean that the simple Planet 9 model needs to be revised. Either way, you're operating right at the limit of what those old surveys can reliably tell you. So with all these searches coming up empty or ambiguous, why don't we just say, we didn't see it, therefore it's not there, and move on? Because we didn't see it only has power if the search was genuinely sensitive to the thing you're ruling out. Surveys like Pan-STARRS and the Dark Energy Survey have imaged large areas of sky very deeply, and they have not turned up an obvious Planet 9 candidate. That matters, it pushes on the hypothesis, but you have to look at how those surveys were designed. They weren't built to hunt ultra-slow movers at high ecliptic latitudes. Their cadence is tuned for things like supernovae, asteroids, and distant galaxies. They have seasonal gaps, they reach different depths in different parts of the sky, and they don't always hit the most likely Planet 9 region at the right times. On top of that, many of these surveys focus near the ecliptic or in certain declination ranges. Parts of the southern sky that current Planet 9 models like best are simply not covered as deeply or as frequently as you'd want. When you fold in all those details, the null result becomes more nuanced. It doesn't say there is no Planet 9 anywhere. It says, if Planet 9 exists, it cannot be in these parts of the sky at these distances brighter than this limit, because we would have seen it. That's why right now the community sits in this balanced position. The lack of a detection is important. It shrinks the allowed hiding space, but it does not yet deliver a clean death blow to the idea. So the tension keeps building. The more we look and don't find it, the more restricted the possibilities become. At the same time, every new deep search for Planet 9 tends to discover more distant small bodies instead, and those new orbits can either support the case or undercut it. Which means the next logical question is this: when we look at all those discoveries from Subaru, from dedicated outer solar system surveys, and from projects like OSOS and DES, are we seeing a consistent picture building up, or is the evidence for Planet 9 starting to crack? If Planet 9 is really out there, shouldn't the biggest telescopes already be closing in, turning maybe into there it is? That's exactly what a lot of observing time has been spent trying to do, and the story so far is messy, not clean. Telescopes like the 8.2-meter Subaru in Hawaii have run dedicated Planet 9 searches. The basic strategy is simple on paper and painful in practice. You point at a patch of the likely sky, you take very deep images to reach those faint magnitudes we talked about, you wait, and then you come back and image the exact same fields again, sometimes multiple times. Then you run software to compare the images and look for objects that have shifted just a little between visits, slow movers that fit the speed you'd expect at a few hundred astronomical units. These campaigns haven't caught Planet 9 itself, but they haven't been a waste, not at all. What they've done is expand the roster of extreme trans-Neptunian objects. Every time Subaru or another big telescope finds a new distant body with a large average distance and a detached perihelion, you get another data point for the Planet 9 argument. Does this new orbit fall into the predicted cluster, with its closest approach on the right side of the Sun and the right sort of tilt? Or does it break the pattern? Each discovery either quietly reinforces the case or quietly chips away at it. There's no single magic object, it's the statistics that matter, and Subaru has been feeding that statistics engine with some of the best deep outer solar system data we have. So if big targeted searches are adding more extreme objects, why isn't the Planet 9 case just getting stronger and stronger with time? Because other surveys stepped in and said, wait, when you correct properly for bias, that clustering might not be real at all. The Outer Solar System Origin Survey, OSSOS, and the Dark Energy Survey, DES, both did something very important. Instead of just collecting distant objects and eyeballing their orbits, they built extremely careful models of where and when their surveys were sensitive. They asked, given how and where we pointed our telescopes, what kinds of orbits were we more likely to find, even if the true population was random? When they then compared their Debias samples of trans-Neptunian objects to the Planet 9 clustering claim, their conclusion was blunt. Once you account for their survey footprints and cadence, their ETNOs do not show the same strong clustering. Statistically, their orbits are consistent with no distant giant planet at all, just a random spread shaped by Neptune and early migration. That doesn't instantly kill Planet 9, because OSSOS and DES have their own sky coverage limits, but it is a serious hit to the original neat story from 2016. The beautiful picture of a handful of distant objects all pointing the same way starts to look more like a result of small number statistics and patchy search patterns. Suddenly, instead of the orbits demand a planet, the message becomes, our larger, well-characterized sample doesn't clearly need one. Just when it looked like the debate might slowly fade, a new player arrived and cranked the tension back up again. A sednoid nicknamed Ammonite. In 2025, a team using Subaru announced a new distant object, officially 2023 KQ14, nicknamed Ammonite. It's the fourth known sednoid, joining Sedna and its rare cousins. Its orbit runs from about 66 astronomical units at closest approach out to about 252 astronomical units at the far end, so from roughly 9.9 to 37.7 billion kilometers, around 6.1 to 23.4 billion miles. Here's the problem for the simple Planet 9 picture. Earlier sednoids broadly lined up on one side of the Sun in terms of their perihelion directions, which is exactly the kind of thing a distant shepherding planet can produce. Ammonite doesn't follow that pattern. Its orbit is anti-aligned, sitting on the opposite side of the Sun compared to the original group. That makes it much harder to tell a clean story where a single distant planet neatly herds all sednoids into the same sector. Some researchers read this as a direct challenge. If you need Planet 9 to point all the sednoids one way, and then a new one shows up on the other side, maybe the whole idea is wrong. Others suggest a more complicated story. Maybe the putative planet has a different orbit than we assumed. Maybe there were multiple big perturbers in the past. Maybe Planet 9 once existed and was later ejected, leaving behind a mixed fossil record in the orbits. Either way, Ammonite forces everyone to stop and recheck their assumptions. So where did Ammonite come from, and why does it matter beyond just being another weird object? It came from a project with an appropriate name, Fossil, short for Formation of the Outer Solar System, an icy legacy. This survey is specifically built to read the fossil record of the outer system by finding and tracking distant icy bodies whose orbits still remember what the early solar system was like. The idea is simple but powerful. Each detached object, each sednoid, each distant TNO is like a preserved clue. Its orbit tells you about past encounters, about how far the giant planets migrated, about whether there were extra bodies around that are now gone. If you only had Sedna and one or two cousins, you could always twist a model around them. As Fossil and similar surveys build up a larger and more diverse sample, your freedom shrinks. If, in the end, you see a clean pattern that only makes sense with a Planet 9 type perturber, then the 9th planet is the missing puzzle piece that suddenly makes the outer system click into place. If instead you see a broad, messy spread of orbital orientations and inclinations that can be explained by migration, passing stars, and a heavy early disk, then Planet 9 starts to look like an extra piece, something you're forcing into a puzzle that doesn't need it. Ammonite, with its anti-aligned orbit, is exactly the kind of test case that pushes the models one way or the other. All of that leaves Planet 9 in a very strange position, both scientifically and literally. Right now, some of the dynamical evidence still points toward a distant massive planet. The original clustering signals haven't fully gone away, especially in certain object subsets. New extreme objects continue to be found that sometimes line up with the predictions. At the same time, large, carefully Debias surveys like ETNOs and DES argue that much of the claimed clustering can be explained without any extra planet. And discoveries like Ammonite show that even the Sednoid group, which was supposed to be the cleanest sign, is more complicated than the early story suggested. So the case isn't dead, but it's no longer a tidy "we've basically proved it" narrative. It's a live, high-stakes argument being pulled in two directions. Either we end up confirming a new planet, one that forces us to rewrite the solar system's blueprint, or we end up proving that the outer system's weirdness can be explained without it, which still changes how we think planets form and migrate. And that sets up the next, harder question you have to face. Are we actually seeing the gravity of a real unseen world? Or are we being fooled by the way we discover things, by our own biases, and by alternative explanations that are just now catching up? Are we seeing the pull of a real hidden planet? Or are we just staring at our own biases reflected back at us? That's the core tension right now, and it's not a small technical detail, it's the whole question. Start with the most brutal possibility, the one skeptics like. The clustering in those distant orbits might not be a physical signal at all. It might just be how we look at the sky. Surveys don't cover all directions equally. They avoid the sun, they avoid the worst star-crowded regions, they favour certain seasons, certain ecliptic longitudes, certain declinations. That means you are automatically more likely to find extreme trans-Neptunian objects in some directions than in others, even if the real population is perfectly random. If you then take that biased sample and say, hey, they're all on this side, must be a planet, you might just be measuring your own selection function. That's basically what ETNOs and DES pushed back with. They took their survey footprints, their depth maps, their actual pointing history, and built detailed models of what kind of orbits they were more sensitive to. When they corrected for those biases, and then looked at their ETNOs, the alleged strong clustering largely faded. In their view, once you do the bookkeeping properly, the orbits they see are statistically consistent with there being no distant giant planet at all, just the expected mess carved by the Neptune and past migration. So you've got one camp saying the clustering is physics, and another saying no, it's your telescope schedule. If the bias argument wins completely, Planet 9 becomes much harder to justify. But the story doesn't stop there, because people have also tried to replace Planet 9 with something more spread out, rather than killing the gravitational idea entirely. One alternative is a massive extended disk of distant objects, instead of a single planet. In that picture, you still have extra mass in the outer solar system, maybe a few Earth masses, up to around 10 Earth masses in total, but spread over a broad ring or disk of trans-Neptunian bodies. Their orbits are a bit eccentric and somewhat aligned, and the collective gravity of that disk keeps the ETNOs clustered, the way a heavy ring can tug on smaller particles inside and outside it. On paper, that can reproduce some of the same dynamical effects as a single planet. It's less dramatic, you don't get a new world to name and photograph, but it still gives you extra gravity in the right place. The problem is, we don't see anything like enough mass out there right now. The number and size of known distant objects don't add up to many Earth masses. You can argue there were more in the past and most of it was stripped away or scattered, but then you have to prove that such a disk could survive in roughly the right form for 4.5 billion years, without getting erased by planetary migration and passing stars. So the massive disk is not a free pass either, it just shifts the difficulty. And remember, Planet 9 wasn't invented only to talk about a few dozen weird orbits. It also tries to hit some bonus anomalies at the same time. One big one is solar obliquity, the roughly 6-degree tilt between the Sun's spin axis and the average orbital plane of the planets. In a simple formation picture, The Sun and the planets form from the same rotating disk of gas, so you'd expect them to be almost perfectly aligned. They're not. A distant, inclined, massive planet can, over billions of years, torque the orbital plane of the planets just enough to build that small tilt relative to the Sun's spin. That's a nice extra point in Planet 9's favour. The same models that explain ETNO clustering also naturally create high-inclination objects closer in, including those odd centaurs and TNOs with crazy tilts and even retrograde motion. So if you pull Planet 9 out of the picture, you don't just have to explain the ETNOs differently. You also need a new story for the Sun's tilt, and for the high-inclination populations, and for the detailed mix of detached and Neptune-crossing orbits. You can invoke more complex migration histories, early close stellar encounters, or multiple smaller perturbers, but each of those has to work against the full set of constraints, not just one plot. That's why this has turned into a kind of Bayesian war in the community, a running fight about odds, not about absolutes. Back in 2016, when the first clean Planet 9 paper dropped, Mike Brown casually estimated something like about 90% odds that it exists. That was based on the strength of the clustering signal at the time and how neatly the simulations matched it. Since then, we've had more objects, more surveys, and serious pushback from groups working on Debias samples. Today, that 90% figure is much more controversial. Some dynamicists still feel that when you line up all the anomalies together, ETNO, clustering in certain subsets, solar obliquity, high inclination TNOs and centaurs, Planet 9 is the simplest, cleanest way to tie them into one story. Others argue that once you fold in OSSOS, DES, and updated bias models, the probability drops sharply, maybe even to the point where the planet is no longer the favoured explanation. There isn't a single agreed-on number now. It's a shifting probability, updated every time a new distant dwarf planet is found, every time an infrared search comes up empty, every time someone reanalyzes survey biases. So why does this debate matter to you if in the end the answer is just yes, there's a ninth planet, or no, there isn't? Because the real value is in the tools being built and sharpened along the way. This whole Planet 9 saga is planetary archaeology done with statistics. Instead of digging in rock layers, you're reading tiny deviations in orbits, using small, icy bodies as detectors for unseen mass. It's the same general trick astronomers use to find exoplanets, where they watch a star wobble or dim in a very precise way and infer planets they never resolve directly. Every technique developed to test Planet 9, bias-aware surveys, long baseline infrared searches, sophisticated orbital simulations, clever ways of combining multiple dynamical clues, becomes part of the standard toolkit for understanding other planetary systems. Even if Planet 9 ends up being wrong, the discipline you've built along the way, the caution about bias, the methods for turning faint statistical hints into testable predictions, all of that stays, and all of that gets applied to new questions. Which brings you to the next layer of the story, the part that stretches from the Kuiper belt out toward the Oort cloud. If there really is a distant heavy planet, it shouldn't just tilt things and cluster some orbits. It should also change how comets are fed inward, how the deep freeze reservoirs of ice connect to the inner solar system. So the next question is simple and sharp. If Planet 9 exists, how much control would it really have over the frozen outskirts? And could the long-period comets we see be one more hidden signature of its gravity? When you see a long-period comet diving into the inner solar system, bright tail, dramatic orbit, where did it really start and who sent it on that insane journey? If Planet 9 is real, it's not just tweaking a few distant dwarf planets, it could be running part of the deep freeze logistics for the entire system. Way beyond even Planet 9's predicted farthest point, you hit the Oort cloud. In most models, that thing stretches from maybe 2,000 astronomical units all the way out to something like 100,000 astronomical units, so from hundreds of billions to trillions of kilometers, tens of thousands to hundreds of thousands of billions of miles. That's a spherical shell of icy bodies, loosely bound to the sun, easily nudged by passing stars and the gravity of the galaxy itself. Inside that giant structure, there's the idea of an inner Oort cloud, closer in than the classic outer shell, but still way beyond the Kuiper belt. In some Planet 9 models, this distant planet sits right at the interface. It doesn't live in the Oort cloud proper, but its orbit overlaps the region where the outer Kuiper belt and the inner Oort cloud populations blur together. In that role, Planet 9 acts like a gatekeeper. Over millions of years, its gravity can slowly lift some Kuiper belt objects onto larger, more distant orbits, feeding the inner Oort cloud. It can also do the reverse, slightly lowering the closest approach distances of some inner Oort objects, unfreezing them just enough that they drift back into ranges where Neptune and the other giants can get a grip. That gives you a natural way to mix the two populations. Some of the bodies you see today as very distant detached objects or as long-period comets could be inner Oort residents nudged inward by Planet 9 over insanely long timescales. Instead of a hard boundary between Kuiper belt stuff and Oort cloud stuff, you get a connected system, with a distant planet trading objects back and forth across that boundary. Now look a bit closer in at the comets that actually show up in our telescopes more often. Ecliptic comets, the ones with shorter periods and lower inclinations, don't come from the classic outer Oort cloud. They come from reservoirs like the scattered disk and the outer Kuiper belt. Recent work has asked a simple question. If you add a 5 to 10 Earth mass Planet 9 to those regions, does the traffic of objects into the inner system change in a measurable way? The answer from simulations is yes, it does. A distant heavy planet reshapes the phase space, meaning it changes which orbits are long-term stable and which ones are slowly driven inward. Over hundreds of millions of years, that changes which objects actually become comets we can see. Instead of a smooth, featureless inflow from a static Kuiper belt, you get a more structured system. Certain inclination ranges, certain perihelion distances, and certain orbital orientations become more populated than others, because Planet 9's gravity prefers to send objects down those lanes. The same is true for high-inclination centaurs, those weird bodies that move among the giant planets on orbits sharply tilted, compared to the main planetary plane. Without Planet 9, it's hard to get enough of them in the right inclination ranges. With Planet 9, the distant torques can pump tilts up, then hand those objects off to the giant planets, which scatter them inward onto centaur-like paths. In that picture, Planet 9 is not just another planet, it's a major traffic controller for icy debris, shaping which comets we see and how often. The physical sequence that makes all of this work is basically gravitational pinball, but split into a slow phase and a fast phase. Start with a distant object in the outer Kuiper belt or inner Oort cloud with a closest approach distance well beyond Neptune, maybe 60, 80, 100 astronomical units. On those scales, Neptune barely touches it, but Planet 9 does. Over millions of years, the steady pull from Planet 9 slowly lowers that object's perihelion, its closest approach distance to the Sun. Eventually, after a long secular drift, the orbit shrinks enough that its perihelion crosses into Neptune's territory, around 30 astronomical units, about 4.5 billion kilometers, roughly 2.8 billion miles. At that point, the problem changes character completely. Now the object is in the zone where Neptune, Uranus, Saturn and Jupiter dominate. They don't act slowly, they act through a series of relatively close encounters that can change the orbit substantially in a few tens of millions of years, which is fast compared to outer system timescales. Those encounters can scatter the object inward toward the inner solar system, turning it into a centaur and then possibly a Jupiter family comet, or they can throw it back outward on a new long-period path. The final result is an odd mix of inclinations and perihelion distances, exactly the kind of messy, diverse population we see in real data. The key is that you need both steps. Planet 9 provides the slow, long lever arm evolution that brings some bodies into the reach of the giants. The known giants then provide the rapid scattering that populates the comet families we observe. We're never going to watch that whole story for a single object start to finish, because it plays out over millions to billions of years. There is no movie of a specific ice ball being nudged by Planet 9, then kicked by Neptune, then flung inward. So instead of spectacle, you have to lean entirely on statistics. That's where the Planet 9 idea becomes a very sharp, testable hypothesis. Planet 9-based models predict specific ratios and distributions. For example, they give you an expected fraction of objects that remain detached versus those that get pushed inward to become Neptune crossers. They predict particular distributions of inclinations for high-inclination centaurs and long-period comets, not just some are high, some are low. They also predict preferred ranges of perihelion distances for certain classes of objects, because the slow drift under Planet 9's influence tends to park bodies in certain stable islands. As new wide, deep surveys come online and log hundreds or thousands more distant small bodies, you can build histograms of these properties, simple plots that count how many objects you see in each bin of inclination, or perihelion distance, or semi-major axis. Then you stack those histograms against what Planet 9 models say you should see, and against what no Planet 9, just migration and Neptune models say. The comets and distant ETNOs become the verdict. If their statistics keep lining up with Planet 9 predictions as the sample grows, confidence in the planet goes up. If they drift away from those predictions, the case weakens, and that brings you to an even sharper problem, one that goes beyond orbits and into the history of the entire solar system. If Planet 9 really is powerful enough to reshape comet highways and the deep freeze reservoirs like this, then how did something that massive end up way out there in the first place? Did it form there, get thrown there, or did we steal it from somewhere else? You can't just drop a 5 to 10 Earth mass planet a few hundred astronomical units away and call it done, right? You have to explain how something that big ended up that far out in the first place. That's where things get really tense, because every origin story for Planet 9 rewrites the early solar system in a different, pretty dramatic way. One of the cleanest ideas is that Planet 9 didn't start out there at all. It started much closer in, as the solid core of a giant planet forming in the same region as Jupiter and Saturn. In the early solar system, that region was chaotic. Big embryos, roughly Earth mass and above, were scattering off each other and off the gas giants. In that environment, a close encounter with Jupiter can give a huge gravitational kick. Most of the time, a strong kick either nudges an object onto a new orbit closer in, or throws it completely out of the solar system, into interstellar space. But there's a third outcome. The kick can be strong enough to send the core onto a very wide, eccentric orbit, with an average distance in the hundreds of astronomical units, and a closest approach still a few hundred astronomical units from the Sun, but not strong enough to unbind it fully. In that case, the object is not lost, it's just parked far out on a long period stretched path. Over time, interactions with the gas disk and the other giants can tweak that orbit further, but the key point is, Planet 9 would basically be a failed giant planet core, thrown out of the main system but still gravitationally attached. That explains its mass, its likely composition, and its distant orbit with one chain of events. Another scenario goes in the opposite direction. Instead of starting in our system and being kicked out, Planet 9 could have formed around another star entirely. The Sun was born in a stellar cluster, packed with other young stars. For tens of millions of years, those stars passed relatively close to each other, on the scale of 1,000 astronomical units or so. If one of those neighbours carried a super-Earth or mini-Neptune on a wide orbit, a three-body interaction could have stripped that planet away and left it bound to the Sun instead. In that capture picture, Planet 9 becomes an adopted planet. It didn't form in our disk, it was imported. That naturally explains a high inclination and a large eccentricity, because the captured orbit doesn't have to line up with our planetary plane. It also fits with what we see in exoplanet system, where super-Earths and mini-Neptunes on weird orbits are common. The trade-off is, you're relying on a specific kind of close encounter in a narrow time window, while the Sun was still in its birth cluster. Statistically, that might be rare, or it might be fairly normal, we don't fully know yet. A third possibility is the pure in situ route, build Planet 9 basically where we see it. That is the hardest to make work. At distances of 400 to 800 astronomical units, the original protoplanetary disk around the young Sun was very thin. There wasn't much solid material per cubic kilometre. Growing a 5 to 10 Earth-mass planet by slow collisions and mergers of big icy bodies at those distances would take longer than the gas disk survives. The gas disk only lives a few million years before it is blown away by radiation and stellar winds. After that, growth slows down even more. Some models try to rescue this idea with something called pebble accretion. In that process, small icy grains a few centimeters across drift through the gas and can be swept up very efficiently by a growing core, much faster than you get with only big collisions. If the drift rate and the core mass are just right, you can, in theory, grow a Planet 9-sized object in the outer regions before the gas disappears. But it's a narrow, fine-tuned path. You need the disk mass, the grain sizes, and the turbulence levels to line up just so. So in situ growth is not impossible, but it demands a much more massive and dynamic outer disk than we usually assume. Then there is the rogue planet angle. We now think free-floating planets, not bound to any star, are probably common in the galaxy. They can be ejected from their birth systems in dynamical fights, or they might even form directly from collapsing gas clumps. If one of those rogue planets wandered close to the young sun early on, the sun's gravity could capture it into a wide eccentric orbit. In that case, Planet 9 would be more like an exoplanet parked in our backyard, a random catch that tells you something about how many rogue super-Earths are drifting through interstellar space. This scenario is similar to the capture from another star idea, but here the donor star is effectively none. The odds depend on how many rogue planets there really are, and how dense the sun's birth environment was. Again, not impossible, but it leans heavily on population statistics we were still trying to pin down. All these stories sound very different, but they share one important thing: none of them are quiet. An ejected core means a violent, unstable early phase where giant planet embryos were flung around like shrapnel. Capture from another star means the sun's birth cluster was dynamically active and tightly packed. In situ growth at hundreds of astronomical units means the outer disk was far more massive and efficient at building planets than our standard models assume. Rogue capture means the galaxy is full of free-floating planets and the sun got lucky. Or unlucky, depending on how you look at it. The good news is, these scenarios don't just differ in their narratives, they should leave different physical signatures that we could, in principle, measure one day. If Planet 9 is an ejected core from near Jupiter and Saturn, its composition might resemble Uranus and Neptune, a mix of rock and ices with a thick hydrogen-helium envelope, a certain density range, and particular atmospheric ratios of elements like carbon and nitrogen. If it was captured from another star, its bulk density and volatile content could be very different from what you'd expect from our disk, maybe richer or poorer in certain ices, hinting at a different birth environment. If it somehow grew in place in the far outer disk, that would imply the early solar system had a lot more mass in that region than we think. In that case, you might also expect to see a rich population of leftover small bodies on related orbits, the debris of that growth process. And if it's a captured rogue, you might see properties that don't fit cleanly into any local story at all, forcing you to think in terms of generic exoplanet populations instead of just solar system formation. So if we ever detect Planet 9 directly, and we manage to measure its mass, its radius, and even get a first look at its atmosphere through spectroscopy, we're not only answering, does it exist? We'll be choosing between radically different histories for the entire solar system. Each data point, how massive, how big, how dense, what gases in its sky, will be a clue to whether our system kicked this thing out, stole it, built it in place, or grabbed it as a wanderer. And that naturally sets up the next question, the one that makes all of this feel much more real. If this world is out there, cold, heavy and distant, what would it actually be like to be there? What would you feel under your feet? How heavy would you be? How dark would the sun look in that sky? You hear distant super-Earth, and you probably expect a place where you'd be crushed flat instantly, right? Some ridiculous gravity that pins you to the floor. The funny thing is, if Planet 9 is roughly what the models say, your body would barely notice the difference compared to Earth. Take a typical case people use in the papers, around 6 times Earth's mass and about 2.5 times Earth's radius. Surface gravity goes up with mass, but it goes down fast when you spread that mass over a bigger radius. If you imagine taking Earth's gravity as 1 unit, 1g, then bumping the mass up by a factor of 6 but stretching the radius by 2.5 makes those two effects almost cancel. You end up with a surface pull very close to 1g. In plain language, you step onto Planet 9 in that configuration, you weigh almost exactly what you weigh on Earth. Your knees don't buckle, your steps don't feel heavy, your muscles don't scream. Now take a slightly bigger version, say 10 Earth masses and 3.5 Earth radii. You've multiplied the mass by 10, but you've also inflated the radius by more than 3. That bigger radius really cuts down the surface gravity. Run the same logic and you drop to something like 0.8 times Earth's gravity, roughly 80% of what you feel here. You would weigh about 4/5 of your Earth weight. That's closer to the Moon's artificial gravity seen in a sci-fi movie than to anything like Jupiter's 2.5g crush. So despite being several times more massive than Earth, Planet 9's surface gravity could feel surprisingly mild, somewhere between basically Earth and noticeably but not dramatically lighter. So if the gravity doesn't kill you, what does the place actually try to do to you instead? The real killer out there is the environment. At hundreds of astronomical units from the Sun, the equilibrium temperature plunges to somewhere around 40 to 50 Kelvin, so about minus 230 degrees Celsius, roughly minus 380 degrees Fahrenheit. That's colder than liquid nitrogen. Any exposed metal, plastic or human tissue would snap and shatter if you let it get down to that temperature. You're in a thermal environment where heat leaks away from you incredibly fast. And Planet 9 is probably not a bare rock anyway. If it's a mini Neptune, which is what the mass and radius estimates suggest, it likely has a thick hydrogen-helium atmosphere over an icy mantle, maybe with water, ammonia, and methane deep inside. You don't come down on solid ground, you come down into a deep, opaque atmosphere. The surface would be some arbitrary pressure level in the gas, maybe with high-altitude haze layers like Neptune's. The planet still has internal heat left over from formation, so those cloud tops might glow faintly in the infrared, but to your eyes it would just look like endless dark clouds in a very dim sky. Photosynthesis as we know it doesn't stand a chance. Any human presence there means heavy gear, pressurized habitats, active heating, and probably floating platforms sitting in the upper atmosphere rather than bases on rock. You're not going for a hike, you're living inside a machine. If the air is that brutal and the atmosphere that thick, what does the day actually look like? How bright is the sun from that far out? Put Planet 9 at 600 astronomical units for a moment, roughly 90 billion kilometers out, about 56 billion miles. Sunlight falls off with the square of the distance. At 600 times farther than Earth, the light is 600 times 600 weaker. That's a drop by a factor of 360,000. The sun is still the brightest thing in the sky, but it is just a brilliant point, only modestly brighter than the brightest stars look from Earth. If you hold your hand up, you won't see a sharp shadow. The whole scene around you would be darker than any natural night you've ever experienced here. The overall illumination at the cloud tops would be way below full moonlight on Earth, closer to the level of faint starlight. Your eyes would be in permanent dark adaptation mode. The Milky Way, if you could see it through gaps in the atmosphere, would be razor sharp. The term daylight almost stops making sense. You're basically an eternal deep night with one very bright star on one side of the sky. Every activity, every piece of work, every landing or launch needs artificial lighting as standard, not as a backup. Now flip the view and think about leaving. If you launch a rocket from Planet 9, how hard is it to get off this thing compared to getting off Earth? The key number is escape velocity, the speed you need to reach so that gravity can't pull you back down. On Earth, that's about 11.2 kilometers per second, around 25,000 miles per hour. For our 6 Earth mass, 2.5 Earth radius Planet 9, the stronger mass and bigger size push and pull in opposite directions again. When you combine them, you find the escape speed at the surface is roughly 1.5 times Earth's. So you're talking about something like 17 kilometers per second around 38,000 miles per hour to get completely free. For a launcher, that's tougher but not insane. You're still in the same general engineering regime as Earth, just with a bit less margin. You're not facing Jupiter's huge escape speed, where the requirement jumps so much higher. A launch stack from Planet 9 would feel familiar to an engineer used to Earth launches, just scaled up a little. The G-loads during ascent might be similar too. A few Gs for a crude rocket, maybe a bit more for an unmanned probe. To give you something human to latch onto, a fast horse runs at about 15 meters per second, roughly 34 miles per hour. Escape from Planet 9 needs you to go over 1,000 times faster than that, not counting any extra delta V you need later to reshape your orbit around the Sun. So it's absolutely not something you do with low-tech hardware, but it's not beyond what we already designed rockets to handle at 1G. All of that is hypothetical unless you can actually get a machine there. So how long would a real mission from Earth take if we decided to go after this thing? Mike Brown and others have played with trajectory calculations and come up with a rough answer. With aggressive mission design, using a close flyby of Jupiter, or even a powered slingshot around the Sun to gain extra speed, you could in principle send a probe to a Planet 9 sitting around 300 astronomical units away in about 20 years. That's similar to the time it took Voyager-class probes to reach the outer planets, but you need more extreme navigation and propulsion choices to make it work. In distance, you're asking a spacecraft to cover tens of billions of kilometers, tens of billions of miles, at a typical cruise speed something like 15 to 20 kilometers per second, about 30,000 to 45,000 miles per hour. That's fast by human standards, but totally normal in deep space mission planning. The catch is the timescale. You launch as a grad student or a young engineer, you get mid-mission data in the middle of your career, and you maybe see the close-up science near retirement. Planet 9 is reachable, but it stretches missions onto human lifetime scales. And that leads to a bigger, system-wide question. If a single distant planet can have Earth-like gravity, deep freeze darkness, and mission times measured in decades, what does adding it to the solar system do to the rest of the structure we thought we understood? The Sun's tilt, the outer belts, even how normal our system looks compared to exoplanet systems. If Planet 9 is real, it doesn't just add one more dot to the solar system diagram, it changes how the whole diagram makes sense. Start with something really basic that has bothered people for a long time, the Sun's tilt. The Sun's spin axis is tilted by about 6 degrees relative to the average plane of the planetary orbits. If everything formed calmly from one collapsing disk of gas and dust, you'd expect the Sun's spin and the planet's orbits to be almost perfectly aligned. They're not. On its own, that's an awkward detail that standard models kind of just live with. A distant massive planet on an inclined orbit gives you an easy way out of that problem. Over billions of years, the combined gravity of Planet 9 and the Sun can torque the orbital plane of the known planets. The key is the long lever arm. Because Planet 9 would be hundreds of astronomical units away, its pull acts like a slow, steady wrench on the average plane of the planetary system. It doesn't really tilt the Sun's spin, instead it gradually tilts the orbital plane of the planets relative to the Sun's spin. After 4.5 billion years, you can build up a 6-degree offset without wrecking anything else. That's a clean, simple explanation for something that otherwise just sits there and looks weird. Now look at the smaller bodies in the outer system. Without Planet 9, it's genuinely hard to make a big population of objects with orbital inclinations above 60 degrees, especially if their average distance from the Sun is less than about 100 astronomical units. You can get a few oddballs from strong encounters and migration, but not the numbers we see. When you run simulations with Planet 9 plus Jupiter, Saturn, Uranus and Neptune, those high inclination orbits show up naturally. The slow secular pumping we talked about earlier slowly increases the tilt, and once those objects wander into the zone of the known giants, scattering locks in a wide range of inclinations, including very steep and even retrograde paths. When you then look at the real sky, you do see trans-Neptunian objects and centaurs on these bizarre orbits, cutting across the planetary plane at extreme angles. They are not the majority, but they're clearly there. In models without Planet 9, they're hard work. In models with Planet 9, they're a side effect of the same dynamics that give you ETNO clustering. That's another point where the Planet 9 picture ties multiple anomalies together with one mechanism instead of separate ad hoc fixes. You might hear all this and think, hold on, if this thing is 5 to 10 times Earth's mass, way out there, doesn't it risk destabilizing the inner solar system? That's a fair worry, but simulations say no, as long as its closest approach stays safely beyond about 200 astronomical units. At that distance, the gravitational coupling between Planet 9 and the inner planets is weak. The rate at which it can shift their orbital parameters is small, and crucially, it doesn't hit strong resonances with Earth or Mars. The inner planets' orbits precess. They slowly rotate and wobble, but they already do that from the known giants and mutual interactions. Planet 9 would just add a small extra contribution. You can have a massive outer perturber rearranging the Kuiper belt and the distant comet reservoirs without kicking Earth out of its safe, stable zone. Zoom out to the exoplanet view, and Planet 9 suddenly affects how normal you think our solar system is. When we look at other stars, we find that many of them have super-Earths or mini-Neptunes, planets between about 2 and 10 Earth masses, on orbits inside where Mercury is in our system. From that perspective, we are the odd ones out. 4 small rocky planets, then gas and ice giants, with nothing in between. If Planet 9 exists, we actually do have a super-Earth. It's just not close in. It's been thrown or placed onto a wide, cold orbit. That flips the story. Instead of, our solar system is special because it doesn't have a super-Earth, you get, our solar system's fairly typical, but its super-Earth ended up way out in the suburbs. That changes how you compare our system to the exoplanet statistics. We stop being the clean exception and start looking more like one of the crowd with a dynamic history. Put all of this together, and you see why Planet 9 is such a big deal for formation theory. If it's real, it forces a new standard model for how the solar system came together. You need early giant planet migration. You probably need ejected cores, maybe capture events, and a much more violent outer disk than the old gentle picture. Planets don't quietly form in place on neat near-circular orbits and then just sit there forever. Instead, cores form, interact, scatter. Some move inward, some move outward, and some are thrown out entirely, and one of them might have been caught on a distant long-period path. The funny thing is, even if Planet 9 turns out not to exist, that more chaotic view of planetary systems is still winning. Exoplanet discoveries show us systems with hot Jupiters, warped disks, resonant chains that later broke, and super-Earths packed close to their stars. The calm textbook solar system was always too simple. Planet 9 is either one more big piece in that chaotic picture, or it's the hypothesis that pushed us to finally admit how messy planet formation really is. And that brings you to the next key angle in this hunt. If a distant planet is out there, freezing in the dark, it's not just reflecting the sun's light, it's also leaking its own internal heat. So the obvious next question is, instead of staring at the sky in visible light and hoping to catch a faint moving dot, how far can we get by listening for its warmth in the infrared? And have we already almost seen it without realizing? If Planet 9 is that cold and that far away, how do you even hope to see it, when reflected sunlight it has basically died out by the time it gets there? This is where you stop thinking like a photographer and start thinking like a thermal camera. Reflected sunlight drops off brutally with distance. Double the distance, you get only a quarter of the light. Put a planet 600 times farther from the sun than Earth, and it gets only 1 part in 360,000 of the sunlight we get here. In visible light, that means Planet 9 is almost invisible, a tiny fraction of Pluto's brightness. But the planet isn't just a mirror, it has its own internal heat. A mini Neptune out at hundreds of astronomical units, sitting at maybe 40 to 50 Kelvin, still emits thermal radiation, especially in the far and mid-infrared, at wavelengths from a few tens to a couple of hundred microns. That's the key advantage of thermal emission. You're not just seeing reflected sunlight, which gets obliterated by distance, you're seeing the object's own warmth, which fades more gently. Space missions like IRAS in the 1980s and Akari in the 2000s scanned the entire sky in these far-infrared bands. They produced all-ski maps where a distant cold planet would show up as a faint point source. If you then compare those maps across decades, a true Planet 9 should shift slightly between the IRAS and Akari epochs, moving a tiny amount against the background galaxies. That's exactly what a 20 to 25 study tried to exploit. The team took advantage of the 23-year baseline between IRAS and Akari, and they searched specifically for objects moving at rates consistent with distances of roughly 500 to 700 astronomical units. That's the sweet spot for classic Planet 9 models. They tuned their expectations to masses around 7 to 17 Earth masses and heliocentric distances in that 500 to 700 astronomical units range, then combed the catalogues for pairs of infrared sources that could be the same object moved slightly on the sky. After a lot of filtering, they ended up with 13 possible pairs and, after image checks, one good candidate, a faint source that appears in IRAS, then shows up in Akari at a slightly shifted position after 23 years. On paper, that fits the Planet 9 idea nicely. In practice, it's not enough. 2 detections, decades apart, are too few to lock down a secure orbit. Later discussion pointed out that the inferred path and tilt might not match the standard Planet 9 predictions very well. Brown himself has said this candidate is almost certainly not Planet 9, and might even contradict the original model if taken at face value. So the IRAS Akari hunt did what good science often does. It gave you a tantalizing maybe, and at the same time underlined how close to the limit of those old datasets you're working. It didn't deliver a confirmed planet, but it did tighten the constraints on how bright such a planet could be in those bands, and still hide. On a different part of the infrared spectrum, the WISE mission adds another layer of constraint. WISE scanned the sky at shorter IR wavelengths, and its data have already been used to show that there is no hidden Saturn mass or Jupiter mass body within thousands of astronomical units. That's actually good news for Planet 9 fans, because it fits the idea that if there is an extra planet, it isn't some huge second Jupiter, it's in the 5 to 10 Earth mass range. Any warmer, more massive or closer giant would have lit up in WISE data, and we'd be talking about it as a done deal. Instead, WISE basically says, above a certain mass and temperature, forget it. There's nothing out there in those ranges. Below that, and at larger distances, you need other tools. The first good candidate from the IRAS/Akari study is especially interesting, because it might be telling you something deeper. If that moving infrared source is real, and if its orbit is as highly tilted as some reconstructions suggest, then it does not match the neat, moderately inclined path Planet 9 was originally supposed to have. Brown has openly said that case, it's 100% not Planet 9. And it might even contradict the existing model rather than confirm it. So now the infrared data are doing 2 jobs at once. First, they're answering the blunt question, is there a big warm planet right where the basic models put it? So far, the answer is probably not in the simplest form. Second, they're quietly asking if there is any distant planet at all. Are we even describing it correctly? Or does its orbit and temperature look very different from those early guesses? That's why every new IR analysis matters, even if it comes back with no clear detection. Looking forward, this is only going to get sharper. Next generation far infrared space telescopes, if and when they fly, will be much more sensitive than IRAS, Akari, or WISE. They'll be able to push down to lower masses, colder effective temperatures, and larger distances. That means they'll be able to say things like, there is no 5 Earth mass object warmer than X Kelvin inside Y astronomical units in this part of the sky. Every time they do that, they cut another slice out of the allowed parameter space. So even before somebody finally gets a clean optical image of a faint dot crawling slowly across a set of CCD frames, the infrared observations are already doing a ruthless quiet job. They're trimming off entire classes of Planet 9 scenarios: too massive, too warm, too close, wrong part of the sky. What's left is a shrinking, more exotic corner of possibilities. And that sets up the last big piece of the hunt. If thermal surveys are boxing Planet 9 into a tighter and tighter corner, and wide-field optical surveys are about to turn the whole southern sky into a time-lapse movie, how long can this planet dodge us? Or, more brutally, are we standing right on the edge of a decade where either Rubin Observatory shows us Planet 9's slow crawl, or the remaining space for it to hide collapses to almost nothing? Rubin is basically the moment where the Planet 9 story stops being mostly theory papers and becomes an actual experiment with a yes or no outcome built in. The Vera C. Rubin Observatory in Chile is built around one mission: the Legacy Survey of Space and Time, LSST. It has an 8.4 meter mirror and a 3.2 gigapixel camera, and instead of staring at one tiny patch of sky in insane detail, it will scan the entire southern sky again and again, every few nights, for about 10 years. You're talking roughly 1,000 images per night, about 20 terabytes of data per day, in several filters, reaching around magnitude 24.5 in each visit. Over a decade, that turns into a time-lapse movie of everything that happens in the southern sky, from supernovae to near-Earth asteroids to, yes, very slow, very faint objects hundreds of astronomical units away. Now connect that to Planet 9's fingerprint. You're looking for a faint dot, maybe magnitude 22 to 25, moving very slowly but very consistently against the background of galaxies and stars. Not streaking, not flashing, just crawling. Rubin's cadence and depth are tuned almost perfectly to that problem. Every patch of the southern sky gets revisited regularly, so you can link detections from one night to the next, from 1 month to the next, and see which specks shift by the tiny amount expected for a 400 to 800 astronomical units orbit. Closer asteroids will move too fast, jumping noticeably between exposures. Distant galaxies and quasars will be effectively fixed. Planet 9, if it's in the favoured part of parameter space, sits right in between, slow enough to look static on the short timescales, but drifting in a very specific way over months and years. Some astronomers have pointed out that if Planet 9 really has the brightness and distance that the current models prefer, Rubin could find it in the first year or two of operations, simply as a byproduct of doing its normal survey and running its standard moving object pipelines. The catch is the sheer volume of data. Over 10 years, Rubin will generate something like 500 petabytes. You're not going to have humans clicking through images saying, hey, that pixel moved. This is a software problem. Machine learning and specialized algorithms will comb through the nightly streams, picking out anything that shifts between images. Most of those are going to be junk from the Planet 9 point of view. Near-Earth objects, main belt asteroids, observational artifacts. So on top of the generic slow mover finder, you need targeted searches that focus on the sky regions and motion rates Planet 9 is supposed to have. In practice, you're asking the code to do something incredibly specific. Out of billions of detected sources, track which ones move a few pixels over the course of years, at a speed consistent with a heliocentric distance of a few hundred astronomical units, and in a direction that fits a plausible solar orbit solution. That's like telling a computer, watch every star in every frame for a decade, and tell me if any one of them shifts by a tiny but consistent amount. It's not a job for hobbyist scripts, it's a core science pipeline. Even if that search comes up empty for Planet 9, Rubin is not wasted effort on this question. It's going to open the census of the outer solar system anyway. LSST should discover tens of thousands of new trans-Neptunian objects, a huge number of centaurs, and probably dozens more sednoids and detached bodies in the Sedna and Ammonite class. Every one of those has an orbit, and each orbit is a data point in the Planet 9 debate and in formation models in general. With that many objects, you can finally do the statistics properly. You can check clustering claims with big samples, not a dozen ETNOs. You can map out inclination distributions, perihelion distributions, resonance structures, and see whether they line up better with Planet 9 exists models, or no Planet 9, just migration and early chaos models. Rubin is both a Planet 9 trap and an outer solar system machine. It will tell you something profound about the architecture of the distant solar system no matter how the Planet 9 question turns out. And that's why the next decade is basically a cliffhanger. Rubin has already taken first light images. As the full LSST survey ramps up, the parameter space for Planet 9 will start shrinking rapidly. Over the lifetime of the survey, one of two things will happen. Either a faint dot shows up in Rubin data, moving exactly the way a 5 to 10 Earth mass planet at a few hundred astronomical units should, and the community pivots from "does it exist" to "how do we characterize it and when do we send a probe?" Or Rubin and the next generation of infrared searches cut away so much of the possible hiding space that what's left is tiny, contrived and statistically unattractive, and the community gradually walks away from the Planet 9 idea. This isn't another small tweak around the edges. This is the experiment that can genuinely end the argument. And that leaves one last uncomfortable question hanging over everything. If Rubin, the infrared missions, and the deep surveys all eventually say no planet in the allowed range, what does that negative answer force us to admit about our models, our biases, and the way we read the outer solar system's fossil record? So what happens if all this effort, all the simulations, all the hype, ends with one clear answer: there is no Planet 9 in the allowed range? That's not a small disappointment. That's a big, sharp statement about how we've been reading the outer solar system. Picture this outcome. Rubin runs for a decade. The infrared searches go deeper. Targeted Subaru-style campaigns fill in the gaps. And when you put everything together, you can say with confidence, there is no 5 to 10 Earth mass planet on a long, eccentric orbit between a few hundred and about 1,000 astronomical units. That's not, we didn't find it, so maybe it's not there. That's, if it existed, it's in that parameter space, we would have seen it. At that point, the ETNO, clustering and all the other weirdness can't be blamed on a single hidden world. They have to come from somewhere else. Survey bias, a massive disk we didn't account for properly, past stellar flybys, subtle multi-planet effects, or some combination we haven't fully modelled yet. In that null result scenario, the gravity anomalies don't vanish. The orbits of Sedna, 2012 VP 113, Ammonite, and dozens of other distant bodies are still what they are. The sun is still tilted. The high inclination centaurs still exist. What changes is the explanation. Instead of one big invisible hammer doing most of the work, you're forced back to distributed, more complex solutions. It becomes a problem of many small nudges, not one large one. The first thing that comes back on the table is the massive disk idea. If there's no Planet 9, maybe the outer solar system once carried a huge amount of extra mass in the form of trans-Neptunian objects. Not just what we see now, but many Earth masses worth of icy bodies on distant, somewhat aligned orbits. The combined gravity of that disk could have maintained clustering patterns for a long time, sculpting ETNO orbits without a single dominant planet. Over billions of years, that disk could have eroded. Encounters with Neptune and the other giants, passing stars in the Sun's birth cluster, and the galactic tide could have stripped away most of the mass, leaving behind just the small fraction we see today. In that picture, the anomalies you see now are leftovers of a once massive structure. A null result on planets doesn't erase the dynamical signals, it just moves the explanation from one object to a lot of smaller ones. Then the hard work becomes, can you build a realistic early disk with that much mass? And can you evolve it forward and still match the present-day Kuiper belt, scattered disk, and Oort cloud? At the same time, you'd be forced to take a more detailed look at the giant planets' migration histories. Right now, a lot of simulations use fairly simple migration paths for Neptune and its siblings. Smooth drifts outward, or one or two nice model jumps. If Planet 9 is off the table, some of the weird ETNO and TNO structures might be telling you that Neptune's path was more complicated. Maybe it moved outward in multiple distinct stages. Maybe it had temporary resonances with Uranus, or with other planet-sized bodies that were later ejected. Each phase could capture and then scatter different populations of trans-Neptunian objects into resonances, creating structures that look, statistically, a bit like what Planet 9 would do, but without needing the extra planet to still be there now. That forces modelers to add more steps, more realism, and fewer shortcuts. You can't just say the giants migrated outward and leave it vague. You need to know when, how fast, in what configuration, and with what other bodies involved. You move from a neat one-paragraph migration story to something closer to a messy timeline, with jumps, stalls, and temporary instabilities. It's more work, less elegant, but probably closer to the real ugly truth of how the outer system evolved. And then there's bias. If, as the big Debias ultra-wide surveys come in, the apparent clustering of ETNOs really dissolves, that's not a loss, that's a major win. It would mean that once you properly account for where, when, and how deep we've looked, the most distant objects actually are randomly oriented, or at least consistent with what you'd expect from Neptune and migration alone. That would mean our understanding of survey selection effects is finally on solid ground. That's important way beyond Planet 9. Selection effects run through everything in modern astronomy. Exoplanet occurrence rates, Kuiper belt structure, even how we measure dark energy with distant supernovae in galaxies. If Planet 9 dies because the clustering turns out to be an artifact of how we searched, that's a sign that we have learned to handle those artifacts correctly. Bias stops being just a nuisance and becomes a tool you can trust, something you build into your models from day one instead of cleaning up later. So a hard no on Planet 9 doesn't end the story. It changes the question. Instead of asking, what's the hidden planet, you switch to, what does its absence tell us about planet formation? And that's where the exoplanet context hits again, but in reverse. Right now, exoplanet surveys show that many stars have super-Earths and mini-Neptunes close in. If Planet 9 doesn't exist, then our solar system really does lack any 2 to 10 Earth mass planets at any distance we can reasonably probe. That makes us an outlier. Somehow, our disk either didn't build a super-Earth, or it did and then removed it completely, thrown into the star, ejected into interstellar space, or broken up in early violent interactions. That is a strong constraint. It tells planet formation theorists that whatever process builds super-Earths around other stars either failed here or got interrupted here, and you have to explain why. Was our disk less massive in solids? Did Jupiter and Saturn form early and block inward drifting material? Did a would-be Planet 9 core get ejected entirely, rather than parked on a wide orbit? Every one of those options points to a different early history for our system, and each one has knock-on effects for the asteroid belt, the Kuiper belt, and even Earth's own growth. So a null result on Planet 9 is not a boring outcome. It's a sharp boundary line. On one side, you have a solar system with a distant super-Earth that we add to the map and study directly. On the other side, you have a system that somehow avoided keeping any super-Earth at all, which makes us genuinely unusual in the exoplanet zoo. Either way, you're forced to update how you think planets build, migrate, and survive, and that brings everything to a final sharp edge. Whether the answer is yes, it's there, or no, it's not, the Planet 9 hunt has already changed the way we look at the solar system. The last piece is to zoom out and ask the big question directly. How can a single object, either confirmed or ruled out, completely reshape what you thought you knew about planetary systems? And what does that say about the next few decades of exploration? How often does one possible planet threaten to rewrite almost everything you thought was settled about the solar system? That's the scale of what's on the line with Planet 9. This isn't a tiny tweak, this is one object that, if it's real, flips multiple fields in one shot. Think about what yes, it exists actually means in one go. First, you would add a new class of planet to our own system, a super-Earth or mini-Neptune, 5 to 10 times Earth's mass, sitting hundreds of astronomical units out, tens of billions of kilometers away, tens of billions of miles. Our textbook list of 8 planets suddenly has a heavyweight ice giant ghost anchoring the outskirts. Second, you'd get a direct testbed for super-Earth physics. Not just dots in exoplanet plots, but a real object you can study with imaging and spectroscopy. Third, you get a cleaner way to explain the orbits of the extreme trans-Neptunian objects, the high-inclination oddballs, even the 6-degree tilt between the sun's spin and the planetary plane. One planet tying together a bunch of anomalies that right now feel like separate headaches. Even the mission numbers change your sense of scale. A probe taking 20 years to reach a world 300 astronomical units away, crossing tens of billions of kilometers, tens of billions of miles, forces you to think in almost interstellar terms while still technically staying at home in the solar system. You'd be planning missions that last a career, not a decade, and you'd have to design instruments and power systems that survive in a light level dimmer than any night sky on Earth. Just confirming Planet 9's existence pushes our engineering, our patience, and our mental picture of where the solar system really ends. Right now, when people talk about super-Earths and mini-Neptunes, it's mostly numbers in Kepler and TESS catalogues, radii in Earth units, masses in Earth units, densities, orbital periods in days, all plotted on nice diagrams. They're real worlds, but they're abstract, because they're just transit depths and radial velocity wiggles. If Planet 9 is out there, suddenly you have one of those planets in your own backyard, close enough for direct detection, detailed spectra, maybe even a dedicated flagship mission with an orbiter or a flyby. At that point, all the physics you've been doing in the abstract, in metric, becomes directly grounded. Mass-radius relations, internal structure models, atmospheric scale heights, thermal evolution curves, all of it can be tested against a real object where you can actually measure the mass and radius independently and see the atmosphere in detail. You'd learn what a 5 to 10 Earth mass, cold mini-Neptune really looks like from the inside out, how its atmosphere behaves at 40 to 50 Kelvin, how its cloud layers form in that deep freeze. Then you'd be able to go back to exoplanet catalogues and say, okay, planets that look like this in the data probably have interiors like that, with much more confidence. But here's the twist. Even if Planet 9 never shows up, the way we've hunted it has already opened up a new style of science, a kind of gravitational archaeology. We're learning to read faint signatures in orbits as if they were fossils in rock. Tiny deviations in the paths of distant ice balls, subtle patterns in inclinations and perihelion directions become clues about unseen mass, past migrations, and encounters that happened billions of years ago. To get this far, astronomers had to get very serious about survey biases, about how often the sky was scanned, how deep in which directions. They had to combine infrared data sets from different decades and look for tiny shifts. They had to design algorithms to trawl through sky movie data from telescopes like Rubin, linking faint detections into slow, coherent tracks. All of that is reusable. The same methods will be used to look for other distant bodies, for signs of past stellar encounters in the Oort cloud, and even for exoplanets and dark matter structures via their gravitational effects. Planet 9 pushed us to treat gravity itself as a historical record, and that lesson doesn't go away if the answer is no planet. And you're right in the middle of that timeline. A few decades ago, we didn't have deep, wide digital surveys. We didn't have all-sky infrared maps at this quality. We didn't have the computational power to run billions-year simulations with thousands of test particles and realistic migration histories. The idea of a statistically strong Planet 9 claim would have been basically unreachable. A few decades from now, Rubin and its successors will likely have delivered a verdict. Infrared missions will have shaved down the allowed parameter space even further. The question will probably be closed one way or the other. You're in the narrow window where Planet 9 is in this strange, quantum-like limbo. It's not real, it's not disproven. It's a live hypothesis that is strong enough to be worth massive effort and weak enough that no one will accept it without direct detection. Every new dwarf planet discovery, every null result from an infrared search, every update from Rubin moves the odds a little. You're watching a rare high-energy scientific argument play out in real time, with clear, testable predictions on the table. So when you hear Planet 9, don't file it away with fringe myths or clickbait headlines. Treat it for what it actually is, a precise, testable claim. There might be a 5 to 10 Earth mass planet on a long, inclined, eccentric orbit, hundreds of astronomical units from the Sun. That claim has been built from hard orbital data and then hammered by other hard data. Either the next decade adds a new world to our solar system, tens of billions of kilometers out, whose gravity has been quietly editing comet paths and dwarf planet orbits for billions of years, or it shows us that the patterns we thought we saw were combinations of bias, small number statistics, and an outer system that is complex in ways we didn't fully appreciate. In both cases, the comfortable flat 8-planet diagram you grew up with is gone. Either there's a hidden giant we're about to catch, or there isn't, and its absence is telling us that our formation models, and maybe even our idea of how common super-Earths really are in systems like ours, need work. The solar system turns out not to be the simple, well-mapped place you were promised, and that uncertainty, that sense that the map might still be missing something huge, is exactly what makes the Planet 9 hunt worth watching all the way to the end. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.